Hello, this is Mr. Steinerson, and in this lesson we'll be going over how to use friction as one of the forces, combining with your other net forces to create net force equations, and do calculations to find acceleration and other things in problems. So we'll take a look at a few examples. Please have a piece of paper ready to write down the examples and take notes as we go through them together. In the first example, we're going to take a look at how free body diagrams help us identify the forces that are acting on an object. For example, if we take Santa's sleigh and we know it's moving across the snow, being pulled by a reindeer, the key information here that we want to pay attention to that will help us draw our free body diagram is the fact that it's moving at a constant velocity of 5 meters per second. Therefore, we know the net force must be zero. So when we take a look at the forces that are acting on the sleigh for the free body diagram, we know that weight is the downwards force. So I'll draw that in. Make a prediction about any other forces that are acting on the sleigh. You should also have the normal force. The normal force balances the force due to weight because the sleigh is not sinking into the snow. It has reached an equilibrium, therefore there are balanced forces in the vertical direction. We also know there are balanced forces in the horizontal direction because it's moving at a constant speed. So the force from the reindeer must also be balanced by the force of friction between the sleigh and the snow. If that wasn't true, if these two were not the same size exactly, there would be an acceleration. So if the reindeer force happens to be greater, then the acceleration would be in the rightwards direction. If the friction force was greater, then the acceleration would be in the leftward direction, and so on and so forth. So use your clues. Constant velocity means that the net force is zero, so therefore these forces must be equal. So what are we learning? Well, we know the force opposing the motion between objects that are in contact is friction. Okay, so anytime we have that opposing force, and there's clues here as well, the opposing means it's moving in an opposite direction. So that'll help you find the force on your free body diagrams, thinking of that word opposing. We have types of friction that we're going to take a look at. There's static friction and there's kinetic friction or sliding friction. For static friction, things are not moving, and so it's might need to you might hear phrases like we have to overcome the friction in order to get the object to accelerate. That is the static friction that you're overcoming because it isn't moving yet. Kinetic friction, kinetic of course means motion, so that's when the object is moving, when it's sliding. It will be less than the static friction. And so a lot of times when you look at the total amount of friction acting on a surface, whether they be a book sliding across the table, you'll see a big spike for the static friction, and then once the object starts moving, it levels off, and it will then maintain that kinetic friction. All right, so how do we calculate friction? Remember our key terms here. We have force weight, force normal, the force sub F is the force of friction, and then F could be any other forces that are acting on it. It could be applied forces from like the reindeer in the last example, or even just a component of a gravitational force. So we're going to take a look at all the forces to help us calculate friction. The weight force is calculated by taking the mass times the acceleration of gravity. The normal force is perpendicular to the surface. If it's horizontal, remember it equals the weight. The force of friction, however, can also be calculated, and the way we're going to do that is we're actually going to be using something called a coefficient of friction. So the force of friction, F sub F, is equal to the coefficient times the normal force. Okay, and I'll be talking more about that in some examples, but please add that to your notes. So it's important that we identify what that normal force is because it's going to help us find the force of friction in our problems. All right, so here's the equation that I just wrote on the last slide. So force of friction is equal to this mu symbol, which stands for the coefficient of friction, times the normal force. The coefficient of friction depends on the surface that you're using, and that is causing the friction between the two objects. So it tells you kind of how sticky the surface is in real layman's terms. But there is a coefficient for static friction with the mu sub s and one for kinetic friction, mu sub k. Often, if you need to know this number, you're either going to calculate it, and we'll show you how to do that, or you're going to look it up in a table. But it does depend on the surface. So the coefficient of friction depends on the surfaces involved. All right, so now let's take a look at an example. If we want to find friction between Santa's sleigh, if it's loaded up for toys and it has a total mass of 2,000 kilograms, what is the static friction force that must be overcome if the coefficient of static friction between the sleigh and the ice, it's always between surfaces, is 0.1? All right, so let's take a close look at this. We know the weight force needs to be calculated because we're going to need the normal force, right? Because that's going to help us figure out what that frictional force is, all right? So remember, coming back to our equations that we just talked about, the force of friction that we're solving for is equal to the coefficient of static friction times the normal force normal. To find that normal force, we will need to use the weight, okay? So we have to calculate that first. In this case, the weight force is 19,600 newtons, let's say. The force normal is equal to the weight force because if we go back to our free body diagram of the sled, the force weight is pulling downwards. The force normal, because it's a horizontal surface, is going to equal that weight force, okay? Huge key ideas there that we want to make sure we come back to. All right, now the force of friction we can substitute in. We know the 0.1 from our problem, which is the static coefficient frictional force right here. And we know now the normal force, which is equal to the weight, which is the 19,600. So this will calculate out to be about 1,960 newtons of frictional force. Please take a look at this problem, see if you have any questions, make notes along the way. If you do have a question, please reach out, but there are a few key ideas here that we would continue to come back to in Quest and other homework assignments. All right, here's some of the key ideas that I wanted to reinforce with you, that the first step is often to find the force from friction. We must look at all the forces that are involved, okay? So we might have a weight force that might be related to the normal force. We might need to use the weight force to help us find that normal force. And then we can use the equation coefficient times the normal force, okay? Step two, if there are other forces acting and we want to find the acceleration, we would have to find our net force equation. Because remember, net force is always equal to the mass times acceleration. So if we have a net force, if we sum up all the forces acting in a particular direction, and we multiply, or that we can use that to help us find the acceleration if we divide that net force by the mass. Okay, so that's going to be our key to finding acceleration. So let's go through an example or two with that. All right, so back to Santa, and he's still pulling that sled, and we know the force that he's pulling at is 4,980 newtons. We want to know how fast does the sleigh accelerate if the coefficient of kinetic friction is 0.05. Okay, once again, we're going to go back to that idea of calculating weight. So using our free body diagrams, we know the weight is equal to the normal force. Okay, now that force of friction we can calculate by taking the 0.05 times 1,000 or 19,600, and we get about 980 newtons of frictional force. Okay, so if I'm going to redraw this free body diagram, let's say the frictional force is pointing in this direction. That's 980 newtons. Our downwards force, the force of weight, is 1,960 newtons, and that's the same as our normal force up, 1,960 newtons up here, force normal, okay? And now, if it's really going to accelerate, there must be a force that's causing that acceleration, and in this case, it's this forwards force here, this applied force from the reindeer, and they're telling us how big that is. That force is, let's call it force applied, is 4,980 newtons. Okay, that is not the net force. The net force, remember, is a combination of forces in a given direction. So I have to be really careful here. I can't just plug in this and divide by the mass and get the acceleration. That's not going to happen. I have to combine the positive 4,980 newtons with the negative 980 newtons, and that's going to be the number I'll use. So looking here, the net force is the difference between those, so 4,000 newtons. Now I can plug that in and solve for my acceleration. 4,000 divided by the 2,000 kilograms. Okay, that was the mass of the sleigh, so 2 meters per second. Key ideas here, use your free body diagrams to help you identify net force. Okay, so always come back to those, they really do help. All right, so what are some big ideas that I really want to reinforce with you is that acceleration is 0 when the net force is 0. It doesn't mean that it's just stopped. It just means that it's moving at a constant velocity. So if you have a puck sliding on the ice and the force was already applied on the puck, so it's already sliding at a constant velocity, our free body diagram would look like this, where there's a weight force and a balanced normal force, but there are no other forces acting on it. The net force is 0. It will move because of its inertia. It's already in motion. It's reached its equilibrium. It doesn't need a force to keep it sliding on the ice. That's one way to look at a constant velocity when net forces are 0. Another way to look at a constant velocity when net forces are 0 is you might have an applied force. Let's say you're pushing on an object like a book and you're sliding it across the table. You might have an applied force, and that applied force, let's say, maybe is 150 newtons. However, friction would act opposing that force, and if the velocity is constant, that frictional force would have to equal the same amount. So if your applied force is 150 newtons, your frictional force has to be 150 newtons also. When I add those together, so let's say I take the force applied to find my net force, force applied minus my force of friction, that will equal my net force equation, which is mass times acceleration. In this case, we'd have 150 newtons minus 150 newtons, and hopefully you're seeing this already as I'm writing it out. That net force is equal to 0. So that is another way of solving some of these net force type equations, is remembering that it's not stopped necessarily. It could have a constant velocity, and that's when the forces are balanced out. That's reached that equilibrium. Okay, so we have to think about how are we summing up those forces, and I gave you an example of that in the last one. Remember to look at all the forces. When you're finding F equals ma, the net force is the sum of all forces, and that's equal to the mass times the acceleration of the object. So be careful. Make sure you use your free body diagrams to help you identify what those forces are. Last big idea for this lesson was introducing the idea of finding frictional force using a coefficient, could be static or kinetic, times the normal force. Once again, the free body diagrams will help you identify what the normal force is. If it's on a horizontal surface, it's equal to the weight. If it's at an incline, you'll have to find the perpendicular component. Hopefully this helped give some overviews of friction. Please use your notes from this lesson to help you with Quest and any other homework assignments in the course. Reach out if you have questions as always, and have a great day.